We're going to talk about the fractures in the frame of some mathematical theory of catastrophes. We're going to talk about the properties that we encounter in a fracture. I mean the factors involved in every fracture. So this is not only an emergent property of Bertalanffy. I don't know if everyone knows this, but when we talk about emergent properties of Bertalanffy, we mean a factor and another factor when we combine these two factors and we have new properties that no of the previous factors have before. Is a property of an emergent property of Bertalanffy. So we are talking about, for example, force or pressure. Pressure is force divided by area, and we have a new property. So the pressure is an emergent property of Bertalanffy, and when we combine, for example, pressure and energy, that they are both an emergent property of Bertalanffy, we have like a meta-emergent property of Bertalanffy. So we're going to go through this. The materials and methods that we use are logic and conditional probability. So this is only mathematical derivation, so apodictic derivation, no need of statistics. We use differential calculus and integral calculus for the mathematical derivations, and always Shannon's theory of communication, that is the negative logarithm, negative base 2 logarithm of the number of choices that we have. So the first component in every fracture is what happens in a fracture. We have the bone, could be femur, could be the skull, could be the spine, but we have one component is the force. It's not the same 5 newtons than 1 newton. Then we have the area, is not the same a force in, let's say, 1 square centimeter than the same force in 2 or 3 square centimeters. So we have pressure, that is force divided by area. That is our first emergent property of Bertalanffy. Then we have the Young's modulus and bulk modulus. That is, the bulk modulus depends on the compression of the volume that we have. Here we are talking about the compression of the bone. So we are modeling the bone with a cube. When the fracture, a compression fracture comes, we have here we have that the, let's say, this box goes from here to here, and from here to here, and the compression goes from here to here. So the change is not only the pressure or tension that was applied to the bone, it was the stress, that is a kind of pressure, is force divided by. How do I return to the previous slide?
El rock.
Okay, is force divided by area is pressure, but it's a kind of stress. And when we divide the change in volume, that is, our first volume was x times y times c, but taking from here to here, let's say the x component, that's our first volume. The next volume would be from here to here, taking the x component and multiplied by the same y and c components. But the strain, that is the change in volume divided by the volume, would be, so just the change in volume, that is this, the change in x multiplied times y and times c components, divided by the previous volume that we have. So the bulk modulus involved in a fracture is the pressure, the stress divided by the strain. Then we have what happens specifically at the moment of a fracture, that is, we model this with a hyperbole. The equation of a hyperbole is 1 or whatever number or constant divided by x. But when we multiply it by, let's say, almost a convenient one, that is x minus b over x minus b, we can almost say that is the same as 1 over x, because we cancel the x minus b with the x minus b. But when x takes the place of the value of b, then on the top we have 0 divided by 0, and 0 divided by 0 is undefined, so we cannot say that it's 1. So in that specific point is when this hyperbole, or the value on the y-axis, is the x-axis, this is the y-axis, we have change from minus infinity to plus infinity, is an abrupt change that is modeled by the hyperbole in the moment in which x takes the value of b. So at the time of the fracture, that's what's happening. Then we have, so the factors that are involved in this abrupt change is the force, or force divided by area, that pressure we talked about, and the other is the time. It's not the same putting a pressure or a force or divided by the area in, let's say, a 5-second interval time or in an hour. So in order to have a fracture, we need like the collision of emergent properties of Catasthrophe at the same time. That would be having enough force in a small area in a small interval time. Now, how can we say this in a more elegant way? We have pressure, that is force divided by area. So units of force are Newton, units of area to be square meters or square centimeters, whatever. But if we multiply it by a convenient one, that is something divided by that something, here we use meter divided by meter. We have Newton times meter is joule, that is the unit of energy, and meter square times meter is cubic meter, so we have energy divided by volume is kind of, if we say mass divided by volume, that is density. So instead of just saying mass density, that is what we say when we have mass divided by volume, we say energy density, that is energy divided by volume, like kind of the density of energy that is involved in the bone at that time. And today we're going to do that same thing, but with another convenient one. So we have energy divided by volume. Units of energy are joule, units of volume are square meter, cubic meter. We are going to multiply everything by 1/2 all over 1/2. So we'll be at the end the same thing. So joules divided by second is the unit watt, that is how we measure power. And square cubic meter per second is volume per second, that is the flux of a fluid or a solid. So we could either say that the fracture is a property or is the result of the energy density or of the power of the thing that is hitting the spine or the skull or the bone, divided by the flux of the thing that is hitting the bone at that time. So we have energy density or power divided by flux. So our conclusions are that the force, that the emergent properties of Catasthrophe are the factors involved in every fracture. We model that with convenient ones that we use to multiply and to do mathematical conversions that at the end give us the same result, but in a more elegant and understandable way. And the way in which we do this is only applying biomechanical principles and doing apodictic, logical, and mathematical derivations in which we don't need to do statistics, only apodictic derivations. Thank you.
Questions?
So basically you're saying that the density is proportional inverse to the fracture, correct? So the force is directly proportional to the fracture. So does that mean that as more energy you apply in the force, the chances of having higher fracture is big? So if we go to a motor vehicle accident, when the force is higher and the energy is higher, the potential of fracture is worse. So we introduce that to a patient who has a cervical contusion after a motor vehicle accident. Clinical scenario. And you do an MRI, and the MRI and CT looks normal, chances that the patient has an insult in the spinal cord based on this theory will be extremely high.
Yes.
Correct?
Yes, exactly.
So that is the main reason for that, from the clinical standpoint of view. The patient with cervical trauma under high velocity impact, we need to keep it 24 hours. A trauma of a cranial, a trauma after motor vehicle accident in the brain, you can have a CT normal. After 24 hours, they present with a high contusion, secondary to the velocity and the impact that they have in motor vehicle accident.
They actually need to be second power of the velocity. It would be the energy is 1/2 of the mass times the velocity. So it would be a factor of second power. Not directly proportional, but proportional to the second power of the velocity.
So this is the explanation of why this event happened.
In mathematical ways.
Thank you. Thank you. So we have 3 more lectures.